If you want to build real-world data science skills, you must learn cluster analysis. Don't make the same mistake I did. Early on in my machine learning journey, I focused mostly on predictive models. I mean, honestly, exclusively on predictive models, and I ignored cluster analysis. And that was a mistake because some of the biggest successes I've had applying real-world machine learning is in the sphere of cluster analysis. It's a great skill. It's wildly useful. And in case you're not familiar, cluster analysis is the process of taking your raw data, customers, patients, insurance claims, whatever it might be, all of your rows of data, and then divvying them up into groups or clusters based on similarity. And while that might not sound particularly powerful, it is. Let me give you an example from the real world. Customer segmentation. Customer segmentation is super useful. It's how companies increase how much money they can make, and cluster analysis is a key part of that process. The topic of this video is the mighty DBSCAN clustering algorithm. DBSCAN is one of the most popular clustering techniques for a reason. One, it's relatively simple to understand, and two, it's pretty powerful. So this video is going to teach you how DBSCAN works. It's also going to teach you the Python code that you need using the scikit-learn library to perform DBSCAN cluster analysis. But I'm going to assume that you have some high-level knowledge of clustering in general. And if you don't, there's a video right here up on my channel. You can go ahead and watch that. Just watch the first parts of it. That'll give you the background. The rest of the video is on k-means, which is another clustering algorithm. Feel free to watch that if you would like. However, just the first part is useful for this particular video. Also, if you'd like to follow along, check out the description below where I can send you an email. And in that email, I will include the PDF of all the slides and the Python code as a zip file. So if you want those files to follow along with this video, check that out below. All right, let's go ahead and get started with DBSCAN. So for this crash course on DBSCAN, of course, we're going to need some data. And the data set that we're going to use is a famous one from machine learning, which is the iris dataset. And this is going to be used throughout the slides. It will also be included in the code file that you can get if you opt for me to send you the files. So at a high level, what is the iris dataset? Not surprisingly, it is a dataset about flowers. Iris flowers in particular. And in this case, what we have is a data set of 150 rows where it's divided equally amongst three types of flowers: Setosa, versicolor, and virginica. So 50 of this, 50 of this, 50 of this, total of 150 rows. And each row, or each observation, as it's commonly referred to, consists of these 5 columns, and they are sepal length, sepal width, petal length, and petal width. And if you're not familiar with flowers, because I'm not, not surprisingly wearing the Iron Maiden t-shirt and doing machine learning crash courses, I'm not exactly a green thumb. I don't know a lot about plants. I had to look this up. So I'm going to tell you what all these things mean, just so that you know. All right, so the measurements for each row of data corresponds to what we see here in this image. And this is an image of an iris virginica flower. So a sepal is this thing right here, which I would normally call a flower, but apparently I would be completely wrong about that. So we get the sepal width and the sepal length. Next up, we have the petal. So we have the petal length and the petal width. So this one I get, this one I understood, this one not so much. So those are our 4 numeric measurements. Now, if you remember from the intro, I said that we're just going to go ahead and take our raw data and then put it into groups. But here's the thing though, this data is already grouped. There's this thing called a class label. This is just a machine learning term that says, look, do I have a column? Do I have a feature? Do I have a variable in my data set that actually provides a classification, a label for each row of data? And in this case, we do, right? We have Setosa, versicolor, and virginica. So here's the question. Geez, Dave, why would I ever use a labeled data set to learn how to do cluster analysis? And the answer is labeled data is wildly useful when you are performing cluster analysis at the very beginning of your learning journey, because you can compare the actual clusters, you can compare the cluster results, that's what I meant to say, the cluster results to the actual labels or the actual clusters, and then you can compare and contrast. And that's super useful to understand the trade-offs of clustering algorithms and clustering techniques. And then once you get good using labeled data sets and you're very familiar with the algorithms and how they work and how you optimize them and all that kind of stuff, then you're ready to go for just piles of data that do not have labels. Okay, so we're going to use the iris data set in this particular crash course for that reason. How everything you're going to learn here applies to much larger, more complicated data sets without class labels. So we have our iris data set, and the iris data set is actually provided to us from the scikit-learn library in Python. And in case you're not familiar, the scikit-learn library is the de facto standard library for machine learning using Python. So it's available out of the box for like the Anaconda distribution. It's available with Python and Excel. It's very, very commonly used. So that's why we use it. And what we can see here is that we're going to import a particular function called load_iris from scikit-learn datasets. And we're going to invoke the function and we're going to say, hey, we want you to bring it back the data as a pandas data frame because we like working with pandas data frames. They're pretty awesome. Now, what it comes back is what's known as a bunch object. Now, I don't know why they call it a bunch object, but I'm assuming it's because it's a bunch of data. Maybe. So anyway, we get back a bunch object and we can say, hey, give me the data, and it'll come back in the form of a pandas data frame. So we get that and we store that in a object, a variable that we're calling iris_df. Not a bad name. And if I call head on it, you can see sure enough, sepal length, sepal width, petal length, and petal width. Now notice I'm only getting the first 4 columns back. I don't actually get the class labels back, which is good because for cluster analysis, I can't use the cluster labels. That would be kind of the actual class labels, that'd be kind of pointless. And I've already used some terminology, so I just really want to level set in the crash course the kinds of terms that we use in machine learning, like in cluster analysis. So when we think about our entire set of data, our 4 columns and our 150 rows, 1, 2, 3, 4, 5, up to 150 rows, we consider this, or call this, I should say, our data set, our table, or our data frame. All these are synonymous, right? It's just basically all of our data. And then along the vertical, we have these things that I've mentioned before. We call these columns, or we call them features, or we call them variables, or we might call them dimensions. So I have 4 columns, 4 features, 4 dimensions, all synonymous. And then lastly, we have our rows. And our rows are known as our rows, observations, our examples, or our samples. The names are all synonymous, but what really matters is this conceptually. When you're performing cluster analysis, your rows are items of interest: flowers, insurance claims, patients, customers, devices, donors, whatever it might be. And then the vertical, the features, then describe these things. That's all of our data set and data set terminology. So we're ready to get started talking about DBSCAN. And we can think of DBSCAN as yet another way to cluster. As I mentioned earlier, I've got a video up here on k-means cluster analysis, which is another algorithm. So what makes DBSCAN potentially different than something like k-means? And the answer is in the name itself. So DBSCAN is an acronym that stands for Density-Based Spatial Clustering of Application with Noise. Now that's what I call shock and awe, right? Your boss says, hey, what did you learn over the weekend? I learned density-based spatial clustering of application with noise, or DBSCAN. They're like, whoa, that's shock and awe. But let's break this down. What does this actually mean? Density-based clustering uses areas of low density versus high density to differentiate the clusters. And that's a bit abstract. So on the next slide, I'm going to show you a visual to really cement this idea. Now, because of the fact that DBSCAN uses density to find the clusters, it can find clusters that are arbitrarily shaped. Most clustering algorithms, I shouldn't say most, but a lot of clustering algorithms are very good at finding clusters that are roughly spherical, right? Either maybe like an egg shape or a ball, something like that. But DBSCAN can find all kinds of funky shapes. We'll see in the next slide clusters that look like this, like 2 crescent moons. It can find those just fine. So that's really, really super useful when your data has very complex relationships. And one of the things that we need to understand is, based on the name, that not all of the data points are going to be assigned to a cluster necessarily because of this idea of noise. This is what the noise means. So the DBSCAN algorithm says, look, if I've got nice, beautiful clusters, and I've got this piece of data that's like way outside all the other clusters that I found, I'm going to say, you ruined the beauty of my clusters, so you're not actually going to get assigned to a cluster. If you want to think of it this way, noise points are equivalent to outliers. So it won't give a cluster assignment to outliers. So not all your data will be clustered, but you will also get a designation in your Python code for any row that was not clustered. Every row that was considered a noise point, you can find that out if you'd like. The last thing to know is that if a data point, if a row of data, which is considered a data point in cluster analysis, if a row of data is assigned to a cluster, that is, it's not a noise point, it is going to be assigned to one and only one cluster. Okay. And as I mentioned, k-means is really, really popular because it is very easy to understand and it handles these arbitrary shapes. So its flexibility compared to clustering algorithms like k-means is part of the reason of its popularity. The reason why I have a k-means crash course up here is because in my own personal work, I've rarely needed anything other than k-means or DBSCAN. Usually those two do just fine, one or the other, or maybe even both simultaneously. Great, powerful skills to learn. So DBSCAN is a great thing to understand if you're doing cluster analysis. Let's talk about what a density-based cluster means with a graphic here. So here we have a graphic, and notice that I've kind of helped you out a little bit, right? Like, oh, this is obviously one cluster, and this is obviously another cluster. All jokes aside, the fact is most humans, if not all humans, will automatically see this as being one logical grouping and this as being another logical grouping because of the way our brains detect visual patterns. Okay, this is known as continuity and proximity. Those are the concepts in visual perception. And because of that, we can see these pretty easily. Now, computers can't really do this so well yet. Maybe they will at some point in the future with advances in AI and computer vision. But right now, they don't do this so well. So what DBSCAN does is essentially say, look, where do I have areas of high density? Lots of data points. And remember, a data point is a row in our original data frame. Where do I have lots of dots? And where do I have very few dots? And what we can see here, this is pretty clear, right? This is high density. This is high density. And this is low density, in fact. No density, because there's absolutely no data points at all. So that's the concept, right, of density-based clustering. That's how it can find these arbitrary shapes like this. And as I mentioned, density-based clusters like this, like DBSCAN, are super, super useful when your clusters actually end up being far more complicated than something that's spherical. Now, here's the thing. Geez, Dave, how will I know if I have spherical clusters or weird shaped clusters like this? And the answer is you can't. Quite frankly, you won't be able to know this with any sort of certainty except for the most ridiculously simple of data sets, something like this. If you have 100 columns and 100,000 rows, let's say, you won't be able to know if your clusters are spherical or if they're oddly shaped like this. So it's considered a best practice to try several different techniques. And as I mentioned earlier, and I'll repeat myself, I apologize, between k-means and DBSCAN, that's usually all I've needed, because what I'll do is I'll try k-means, see how well it does, and then I'll try DBSCAN and see how well it does. And if one does better than the other, great. If they both do awesome, maybe I will combine the results to get something even more interesting. Okay. And later on, we'll talk about how you can determine whether or not the clustering results are quote unquote awesome. So here is the DBSCAN algorithm. And an algorithm you can think of as just like a recipe of how to actually do something. So the DBSCAN algorithm is the recipe of how to do the DBSCAN clustering technique. The DBSCAN algorithm is really, really awesome because it's easy to understand because it works with these definitions. For example, as far as DBSCAN is concerned, there are core points. Core points are data points inside of a cluster, which kind of makes sense, right? I mean, they call it core, so it means it's like, if a cluster is like this, let's say, then the core points are obviously like right in the middle of the cluster, right in the center of it. So a data point under DBSCAN is considered a core point if it is surrounded by a minimum number of other data points within a set distance. Think of like a template where you have like a circle like this, right? In this template. And what you do is you go around with a DBSCAN and you look at every single data point, every single row of data, and you say, if I put my current point, let's say I'm looking at row one's right here in the middle of this distance circle. That distance circle can either include or touch a bunch of other data points. And as long as it includes or touches enough data points, then DBSCAN says this point is core. And that's a bit abstract. I'm going to show you in slideware how this actually works. It's super, super easy. So when you set DBSCAN, when you use DBSCAN, you have to set the distance. And this is known as EPS. So EPS is just how big is that distance circle that you move around. And then the minimum number of points within that circle, within the EPS circle, is known as the min samples, right? Because remember, samples is equivalent to rows. Those are synonymous. So how many rows of data have to be within the EPS circle? So that's the first definition. Again, we'll see this in slide where it's very, very intuitive. Next up, we have border points. And a border point is not a core point, which makes sense because it's got a different name. but falls within a set distance of a core point. So if I got a bunch of core points and then I draw a circle around a border point, and as long as that circle, where the border point is in the middle of the EPS circle, as long as that EPS circle touches or contains a core point, then that's a border, which kind of makes sense, right? Imagine those crescent shapes that we saw on a previous slide. Right, some of those dots are obviously in the middle or the core parts of the crescent. And what we're trying to do is identify the edges, essentially, of those crescent shapes. And lastly, we have noise points. And not surprisingly, a noise point is any point that is neither core or border. Super simple. I mean, this is, you'll be surprised you'll be shocked and surprised at how simple this really is. Okay. The DBSCAN algorithm, it labels all data points as core, border, or noise. That's the first thing you do, right? You take your little EPS circle and you move through all the data points and you assign them to be either core, border, or noise. That's the first thing you do. And then you, conceptually, you remove all of the noise points. Now, in Python, don't panic. None of your rows of data from your data frame are actually removed. What you actually get is a cluster assignment of -1. So that cluster assignment tells you it's a noise point. So you don't lose any data. The rows are not gone. Don't panic. It's all good. And then what we do is we say, okay, after we've done that, we connect all of the core points that are within EPS distance of each other. Okay, so let's say I have a core point here and a core point here and a core point here. I just move my little EPS circle and I'm like, oh, those three guys are in a line. They're all connected because they're all really close together. They're all core points. What I'm trying to do is build out all of the core points. And then we say, okay, each group of connected core points becomes a separate cluster, which kind of makes sense, right? As long as you can keep connecting core points, that's all one cluster. Once you can't do that anymore, you've got another cluster, 1 cluster, 2 clusters, 7 clusters, whatever it might be. And then lastly, we're assigning each border point to the cluster based on the proximity to the core points. So if you're a border point, you're going to get assigned to the cluster of the closest core point, which makes sense, right? Because that's you're the edge of the cluster. So that's where you should belong. So that's the basic algorithm. As it turns out, selecting the right values, or more aptly put, or more correctly put, the optimal values for EPS and min samples is a non-trivial problem. So I'm going to give you a resource, a textbook. It's one of my favorite machine learning resources of all time. At the end of this crash course, that textbook will teach you and will tell you about the techniques that you can find to find optimal values for EPS and min samples. Let's talk about a contrived example here so that we can actually understand what's going on. So imagine, if you will, that I've got this hypothetical data set here. And if I ask most human beings to tell me where they see clusters, they would say, look, this kind of looks like a cluster to me, because notice there's a separation here, low density. And then this kidney bean shape thing, they would say, is another cluster. And they'd say, these other guys over here, they're basically outliers. Okay, so keep that in the back of your mind. That's what most humans would see. And what we're going to do is we're actually going to run through in slideware the DBSCAN algorithm using an EPS circle and all the definitions that we saw. And we'll actually see how, in fact, the DBSCAN algorithm clusters this particular set of data. Imagine, if you will, this is my EPS circle. So I've set my EPS value to be essentially the radius, right? The radius of this circle. So if this was an EPS of 1, the distance from the center of the EPS circle to the edge would be 1, and then it sweeps around, just like that, okay? So that's our EPS circle. And for this particular contrived example, we're also going to set min samples to be 4. So the EPS circle needs to touch or encompass, wrap around 4 or more data points for a particular data point to be considered core. Now, in the definition of DBSCAN that's provided with scikit-learn in Python, min samples, this number 4, includes the current data point. So that's a bit abstract, so let's get started. So imagine, if you will, this data point right here, this blue data point, is the data point that we're currently looking at. Because the DBSCAN is going to look at every single data point one at a time and apply all of these rules, all these definitions. So we center our EPS circle on this point, and then we say, all right, cool, let's count up the number of data points that are touched or encompassed by the circle, including the point itself. So 1, 2, 3, 4, 5, 6. All right, so the total number of points, well, actually, let's talk about that. Let's say that this guy, let's say it's kind of hard to see, but let's say for the sake of argument that we don't actually include this guy. So we've got 1, 2, 3, 4, 5. We got 5 here, right? I said 6, but I have 5 here on the slide. And the reason for that is I just remembered is because this guy's actually not covered. All right, so there you go. And 5 is bigger than 4, because remember, we set min samples to be 4. So this is considered a core point. So I'm going to color code core points in this particular contrived example as blue. So this core point is blue because there are 5 data points touched or encompassed by the EPS circle, including the current point that we're looking at. And now all we do is just move the circle. We move the circle around every data point, every row of data. And we say, okay, cool. This is our current point that we're looking at. We draw our EPS circle and we can see, definitely not 4 or more data points contained or touched by the EPS circle. So this cannot be a core point. However, the EPS circle is touching a core point. So this is a border point. Hopefully you're tracking there, right? Previous slide showed what you need to do, what you need to have, the characteristics you need to have to be a core data point in this cluster. And this is the example of what you need to be a border point. And here's the thing. The algorithm just goes and just moves that EPS circle all the way through all the data. And if you do that with this, this is what you get eventually. I took a lot of time and effort to do this by hand, by the way, filling this slide. So hopefully you appreciate that. And notice this. Notice that we have core points here, core points here, core points here. And these two guys actually are neither core nor are border points. So they're in fact noise points. So this is a noise point, 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 based on the definition of DBSCAN. And the DBSCAN algorithm says, cool, once I've done this process of moving the EPS circle all around, it's time for me to remove the noise points. So, boop, there you go. Now, look what's going on here. So once we've eliminated the noise points, we then take our EPS circle and go through each core point. We say, hey, if the EPS circle touches another core point, we link them up, link them up, link them up, link them up, link them up. Oh, wait, that's gap's too big. Start over, link them up, link them up, link them up. Once again with the EPS circle, right? Moving it around. And then over here. And notice what we've got here. Even though most humans with the original data would consider this entire kidney bean one cluster based on the shape, given the parameters that we set for our EPS circle and the fact that we needed 4 minimum samples, we actually get 2 clusters. DBSCAN is going to find the kidney bean divided in half into 2 separate clusters. Not exactly half, but hopefully you get what I mean by that. And then, of course, this guy over here is its own cluster. What's super interesting is now we have to take all of these gray border points and assign them to their appropriate cluster. Now, this is going to be pretty easy, right? All of these guys obviously belong to this orange cluster. And obviously these guys here belong to the purple cluster. But what about this data point right here? Notice that this data point is basically halfway in between these. So if you draw an EPS circle around this, it would touch this guy and this guy simultaneously. So which cluster does this particular ambiguous data point belong to? As it turns out, that's an algorithmic implementation decision. And the way DBSCAN and scikit-learn with Python works is it will assign a cluster, it'll assign a cluster to a border point in this situation based on when the first cluster was found. So if we think that green was done first and then purple was done, then the algorithm will say, as a tiebreaker, I'm just going to assign this to the green cluster because that was the first one that I found. And then voila, DBSCAN has completed the clustering. And that's it. It's literally that simple. Now, you might be wondering, how does it actually work behind the scenes, this EPS circle? So by default, DBSCAN uses something called Euclidean distance to actually calculate whether or not a particular data point is within the EPS circle centered on a particular data point in question, right? So it uses Euclidean distance to create that arc that it swings around to draw the EPS circle. And if you're not familiar with Euclidean distance, check out my video up here, the K-means clustering video, where I do talk about Euclidean distance. There you have it. That's how the DBSCAN algorithm works. And let's talk about some of the caveats, some of the things that you need to know to use DBSCAN effectively. So first up, the DBSCAN algorithm always requires optimization. I'm going to show you in the code in a few slides how to use DBSCAN with the defaults. In practice, you never ever want to do that because DBSCAN defaults almost never will work right. You actually need to set the value for EPS and min samples yourself. You got to do it. And like I said, the textbook that I'm talking about, that I'll recommend, below or later on, that I'll recommend later on, will show you some techniques to find out the optimal values for EPS and min samples based on your particular data set. So as I mentioned, Euclidean distance is the default with DBSCAN and scikit-learn, but you can use other distance metrics. For example, if you are doing something in logistics and you need to take in account the curvature of the Earth in your clustering, you can use something like haversine distance, for example. And if you don't know what any of that means, that's okay. Most of the time in real-world business analytics, you're just going to stick with Euclidean distance, which is the default. Now, DBSCAN is resilient to outliers. right? Because it will define noise points and say, look, if you're too far out of whack, it's good. It's resilient against outliers compared to other types of clustering, like k-means. There is this idea that you might need to standardize your data. And standardizing your data essentially is this idea of running what's known as a z-score through your numeric data to put all of your data on equal footing. So think about whether or not you need to do that based on your distance calculation. DBSCAN can have problems when there are many radical areas of changing density, right? If it's like high density, low density, high density, low density, high density, low density, so on and so forth, the DBSCAN algorithm goes, it's really hard for it to figure that stuff out. And again, you'd be like, Dave, well, how do I know if my data has that? You don't, unfortunately. If you have lots of columns and lots of rows, it's really impossible for you to figure that out totally on your own. Don't worry about that so much. Just try DBSCAN out, see how well does it do. If it does pretty well, great. You've got a good clustering. And if it doesn't, you can always try something like k-means instead. Here's the code. What I'm doing here is I'm going to load up my data. So you can see here that I'm using the load iris, the load iris function from scikit-learn datasets. And I'm getting back a bunch object, like I told you earlier. And then I'm accessing the data from iris bunch. And that gives me the data frame that we saw earlier, right? Where I have the 4 columns and 150 rows. Now, by convention, when you're using scikit-learn, the features that you're going to feed into an algorithm, whether it's a clustering algorithm or a predictive algorithm or whatever it might be, is called _x. That's just the naming convention. So I'm calling this iris _x to be compliant with the naming convention. And now I got my data ready to be clustered. And then what I do is I instantiate a DBSCAN object. Because what I've done here is I've imported the DBSCAN class from scikit-learn cluster, and I've created a DBSCAN object. And once I've done that, I can actually use the class to perform a DBSCAN clustering. So with my DBSCAN object, I call fit on it. Fit is another naming convention in scikit-learn. When you see fit, what you should think in your mind is that, I'm going to go tell a particular class, DBSCAN, k-means, decision trees, random forest, whatever it might be from scikit-learn, to go learn from the data. That's what fit means, go learn. So go learn to cluster the iris _x data frame using DBSCAN. Now, to keep things easy, even though I have 4 features in my data frame, 4 features in iris _x, I'm only going to use 2 for this example. And the reason for that is simple. I just want to be able to visualize the results for you. And if I had 4 dimensions, I can't create a 4D visualization, just doesn't work. So I'm going to use a 2D visualization. So I asked DBSCAN to go fit itself to the data. So it chunks away and it runs and it runs and it runs and it runs. And eventually it gets done. And once it's done, I can ask the object for the labels. Now, if you're not familiar, labels _, that's an attribute. That's what the underscore means. This is some sort of attribute on my object. And what comes back are the cluster assignments. Now, here's the thing. DBSCAN will try and find as many clusters as it can given the value of EPS and min samples. And right here, we're using the defaults. So what we can see here is I'm getting the label assignments and I'm storing them on my data frame, iris _x, something I'm calling label. It's just my cluster assignment label. And now I can say, hey, let's do value counts on that column. And I can see how many clusters did DBSCAN find and how many of the individual rows of data were assigned to one cluster or another. So when I do that, I can see here, first and foremost, that I only get 2 clusters, 0 and 1. And 50 rows of data were assigned to cluster 0, and 100 rows of data were assigned to cluster 1. Notice I do not have any cluster assignments of -1. So -1 would denote a noise point. A particular row of data was thought as being as an outlier and was not clustered. So all of my data has been clustered here because I see no -1s. Now what we can do is say, great, that's awesome. What kind of results happened? And we can see that here. This is the advantage, once again, of using labeled data when you start learning cluster analysis, because you can actually visualize the real clusters vis-a-vis the clustering results. So this is the actual clusters in the data. So we can see we got 50 of this kind of flower, 50 of this kind of flower, and 50 of this kind of flower. And the colors don't really mean anything, just so you know. These are defaults from the Plot9 library, which I use for my visualizations, okay? But what you can clearly see is this is one cluster, this is another cluster, this is another cluster. And now we can compare that actual stuff, the actual data, to what DBSCAN found. And not surprisingly, DBSCAN said, look, this is a cluster, which you would hope it would find, even with the defaults. And it did. And it said, look, this is a cluster. And then it said, look, using the defaults, I just kind of see this as being one big blob. And if you take a step back and think about it, that kind of makes some sense. Because if you didn't know anything about the data set, which you will most of the time, you won't know anything about the data set, right? Because the data won't have class labels because you're just working with raw data. You would, if you graphed it like this visually, you'd be like, yeah, this seems like this might be one cluster, this might be one cluster. But in fact, actually, it's a little bit more complicated than that. So this is a great example of why you need to always, always, always tune DBSCAN. And like I said, I'll give you a recommendation on the next slide here for a textbook that will teach you some techniques for doing that. Because when you compare these results, which in a vacuum would look totally normal and logical, if you compare them to the actual labels, you'd be like, that's a problem. And once again, using these labeled data sets helps you start to understand the trade-offs. So for example, you could go try and optimize EPS, MN samples, rerun DBSCAN, compared to the actual clusters, and that will help you iteratively start learning the trade-offs of all of these types of techniques. Now, with that being said, here's how you continue your learning. This right here is a free book. You can Google it. There's a PDF that you can download off the interwebs, An Introduction to Statistical Learning with Applications in Python. That's the name of it. And this book is great. It's very easy to understand. It's at a pretty high level. And what it allows you to do is learn about a lot of stuff. So it has DBSCAN here, it has k-means, it has a whole bunch of different kinds of machine learning algorithms in it. It doesn't cover anything in too much detail, by the way, but it is free. There's a backing website with some videos that might be useful. Now, if you're serious about getting good with cluster analysis, I recommend this book. You can see I took a picture of it on my dining room table here. This is the textbook that I first learned machine learning from. Many years ago when I got my master's degree in computer science, this was the ML textbook we used. It's a great book. So this is the first edition. I think it's the second or third edition is available now on Amazon. This is a great book. It is a textbook, make no mistake, but you don't have to be a math genius to actually read the book and understand what's going on. There's appendices in the back if you want to learn more of the hardcore math stuff, but you don't have to. And this book is not actually written in Python. It's not actually written in any programming language. So this is a great, great book because it raises the level of abstraction up. It says, look, I'm not going to worry about code. I'm going to teach you the concepts. I'm going to teach you how k-means works and how DBSCAN works, how hierarchical clustering works. How do you optimize all of these clustering algorithms as much as you can to try and get the best results? So this is a great, great book. That's it for this crash course. The next video in the crash course series is going to be on logistic regression. Logistic regression is an OG predictive modeling technique, old school, original gangster kind of. Hopefully YouTube doesn't flag that. So logistic regression is a powerful, well-used technique for doing predictive modeling to allow you to analyze your data where your business question that you're trying to figure out is like yes and no. So when that video is ready, it'll show up on the tile here, as a tile here on the screen. And in the meantime, I'll put up another one of my videos for you to watch in case you would like that. All right, there you go. DBSCAN, learn it, use it, love it. And until next time, I wish you very happy data sleuthing.